Hi folks, we're going to take a look at a question involving sketching the graph of a parent function. So let's take a look at the question we're going to be working on. We've got our function root x, and we want to sketch the graph of y equals -3 times f at 2x plus 4 minus 1. And I also want you to state the domain and range of the transformed function. So as soon as you take a look at your transformed function, I need you to zero in on the input. And if there is a coefficient of x other than 1, even if it's just -1, you have to factor that out. So I'm not even going to talk about anything else until I take care of that. And I suggest you do the same when you're working on one of these problems, either in your homework or on the test. Okay, so now we can start talking about this function here. So it's given in function notation, which is nice because it forces you to focus on the transformations themselves. What it doesn't give you is the operations that have to be followed to find the y values. But that's okay because that's not what we're trying to do here. We want to focus on how points are being transformed. But we may as well look at how we would write this in explicit notation. So here we take a look at our parent function. And it says that it takes the input and takes the square root of that. So the input here is 2 times x plus 2. So it takes the square root of the input. Okay, and then the transformations tell us to take this output multiplied by -3 and then subtract 1 from the output. So this is what this function would look like in explicit notation. So if I did want to create a table of values, this is what I'd be using. But I want to focus in on the transformation, so I'm going to stick with the function notation. So as I described in class, what I want to see is how specific points are transformed. So since our parent function is root x, we had chosen 3 representatives of root x to give us a sense of the shape. So we picked 0, 0, 1, 1, and 4, 2. And we'll see how these points are transformed. So again, we have to follow BEDMAS since we're performing operations on the x and y coordinates. So the first thing we have to take care of are the multiplicative transformations. Okay, so I'm not even going to worry about the additive ones now. So this tells us that we have to multiply the y values by -3, and we have to divide the x values by 2. So let's keep in mind that anytime we're working with a horizontal transformation, we're always performing the opposite operation on the x coordinate. Okay, so let's see what happens. So 0, 0, dividing the x by 2, multiplying the y by -3 has no effect. So this is an invariant point under those transformations, but 1, 1 is not. So divide 1 by 2, so 1/2, and here multiply the y value by -3, so -3. Do the same thing here. 4 divided by 2 is 2. 2 times -3, -6. Now we can take care of the additive ones. So I'll add those in. So -3, so multiplied by 2, but now we're adding in our additive translation here and our vertical one there. Okay, so again, opposite effect. Here if we have x plus 2, the effect is opposite on the x value. So we're going to be subtracting 2 from the x value, and same operation for the vertical one, subtracting 1 from the y value. So this becomes -2, -1. Subtract 2 here, so that's -1.5, -4. And then subtract 2, so 0, and -6 minus 1 is -7. Now that we have the points on our transformed function, we can set up our Cartesian plane. So I notice here everything is negative or 0. I have to get to -7 in the y's, but these x's are pretty small. So I'm going to set up my Cartesian plane to model that. Okay, y and x, -1, -2. And then here we have to go 1, 2, 3, 4, 5, 6, 7. Okay, so let's plot our points. So -2, -1, a point right there. Then -1.5, -4, 1, 2, 3, 4, -1.5. Okay, and lastly we have 0 and -7. Okay, so let's remember that this was flipped over, so instead of going that way, okay, we should be going downwards. So I'm just going to flip the paper around to help me draw my graph a little nicer. So we're going to start from the point that was transformed from 0, 0, the starting point, and slowly try to draw a nice graph. Okay, and I definitely want to give the sense that A, this function continues, so I need the arrow, and that it's not approaching an asymptote, so that it is getting smaller and smaller and smaller. Now that we have the graph, we can easily read off the domain and range. So we see that the domain starts at -2, and all numbers larger than that. So we have our domain is x in R, such that x is greater than or equal to -2. We have to include -2 there. And again, our range we see starts at -1 and goes downwards. So our range will be y in R, such that y is less than or equal to -1. Now say the question was just to find the domain and range. Do you necessarily have to graph the function? You certainly could to help you read off the domain and range. However, you could also start with the function root x, which we know has a domain and range of x greater than or equal to 0 and y greater than or equal to 0. And you could look at the transformations. So you know that there's the vertical reflection, which means that instead of being greater than or equal to the number, it'll be less than or equal to the number. And since it gets moved 2 to the left and 1 down, that will also affect the domain and range. So the domain, instead of starting at 0, will start at -2, and the range, instead of starting at 0, is going to start at -1. So an alternative to actually sketching the whole graph just to find the domain and range.